Cambridge Signal Processing Laboratory, and he will talk about applications of spatial point processes to multi-object tracking.
Thanks, Alan. This talk is going to be about the use of point process theory in multi-object tracking. So I should mention that multi-object tracking is not a new problem, and it's a problem that's been studied in engineering for I should have turned it on. Thanks. So it's not a new problem. It's a problem that's been studied in engineering for about 2 decades at least, and there's a lot of activity in computer science as well. But what's new here is essentially the use of the point process framework to formulate the problem, and the use of some results from point process theory to characterize distributions of interest. And once we have done so, a lot of the computational tools that we actually use to solve our problems with is using sequential Monte Carlo. So there's a big sequential Monte Carlo component to this work. So here's just an application of the problem of multi-object tracking. So assuming not everybody knows about it, what you're looking at here is a sequence of images of a surface of a cell. And these bright spots here are essentially proteins that molecules that have been tagged with fluorophore and are diffusing on the surface of the cell. And essentially, so these are experiments done at chemistry, in fact, by David Kleineman here in Cambridge. And what they do is that they control the environment in which the cells are immersed. And by monitoring the change in the diffusion patterns of these molecules, they can deduce they can glean some ideas concerning the structure of the cell and how it functions. So from a signal processing perspective, to enable them to do what they need to do, what you need to do is you need to track these molecules on the surface of the cells. What you don't know is how many of them there are, and the signal processing challenge is the task is made harder by the fact that, as you can see over time, these bright spots relative to the background fluorescence, which is a speckle, is diminishing. Its intensity relative to the background is diminishing. That's because the fluorophore is bleaching. So essentially, this is an example of multi-object tracking. You don't know how many fluorescent items there are. You want to track the precise paths they take on the surface of the cell. Okay, so what we're going to do now is we're going to abstract away from this application and formulate the problem, and then we'll consider how we actually solve it. So the hidden Markov model is going to feature prominently in this work. So I guess it's best if I go through it. Okay, so in a definition of hidden Markov model, you've got 2 main ingredients. One is a hidden process, xk, which is a calligraphic x valued. So this could be a subset of RD, for instance. And this process is unobserved. Okay, you don't see it. And its initial distribution and it's basically its evolution follows a Markov transition density. So I mean, I don't distinguish between densities and measures in this talk. So I sort of use the same notation for both of them. And this process is observed indirectly through another process y, which is calligraphic y valued. And the important point here is that the random variable yk is basically, its distribution is entirely determined by just what the state xk is at time t. Okay, and this is the distribution this is just distribution by which it's drawn. So, okay, this is just an example. This is, these are 2 mappings. This is how, for example, the state could evolve. You've got a mapping that takes you from the previous state some noise to the new state value. And this is similarly how the observations could be generated as well. And if these mappings were linear and the noise was Gaussian, you would know this as your linear state space model. And the problem we are interested in is filtering. Okay, so when you get your observation record, there are k observations here. You want to compute the sequence of posterior distributions. So now what I'm going to do is I'm going to look at a hidden Markov model where the hidden and observed processes are spatial point processes. So I need to define what a spatial point process is. So a point process on X. So essentially a spatial point process is an unordered set of points where both the position of the points and their number are random. Okay, so the space where the pattern lives is also known as a state space. So but hopefully it won't cause any confusion. And we're only interested in dealing with point processes which are finite. So what this means is that the distribution of the cardinality of the process is limited to the non-negative real numbers. Okay. So now mathematically, I mean, I personally find it more convenient to treat a point process mathematically as a random vector. So what I mean by this is that essentially realizations of the point process live in this space, a disjoint union. And what you need to do, you need to specify the law of the point process, you need to specify two things. One is the distribution for its cardinality. And given a particular cardinality, how many points there are in the realization, you will draw the joint distribution of the location of the points according to the distribution on the product space. But for the conceptual development of the ideas, it's far more convenient to just think of a point process as a random finite set. And to be consistent with this interpretation, this distribution essentially is symmetric. So what it means is that when you draw a realization, the permutation of the realization is so it's basically any permutation of the realization you can actually see. All right. So what you need to do is make sure this distribution is symmetric, and then you are consistent with this interpretation. Well, this is just a minor point for those who are interested. The rest of the talk, we can just think of a point process as a random finite subset. And when I'm also going to talk about superposition. So when I say superposition of two point processes on the same space, I mean just take their union. And the notation I'll use for point processes is essentially capital letters in bold, and their realizations will be small letters in bold. Okay, so the hidden Markov model we want to study is this one. It's essentially no different from the one before, just that the space on which the hidden and observed process are defined is basically different. And the hidden and observed processes are point processes. They will have some law, which I will define in the subsequent slide, that tells us how they evolved. And the problem is, again, the same, that given the realization of observations, you want to compute the filter. And also what you want to do is estimate model parameters. Okay, so there will be some parameters that parameterize the evolution of the process, and this is what we like to do is estimate them as well. Okay, and let's specify now the dynamics. So the hidden process, how does it evolve? Well, let the realization of the process at time k be this. Okay, so I just assume that there are n points in realization at time k, and this is the realization of the individual points. Each point, so we consider xi, the ith point in here. Each point will expire with a certain probability. So what that means is that the point will have no descendant at the next time. Okay, so if it does not expire, it survives, it'll be moved or is displaced or it'll have a descendant, however you want to think about it, and that descendant will be drawn according to this distribution. It's basically a Markov transition on x. Now all this happens independently for every point in xk. And so we see straight away that the realization at time k plus 1 is going to be essentially this process thinned and displaced. But in addition to that, we're also going to augment the realization at time k plus 1 with a set of new points which are drawn, which are unrelated to the points that have survived from the previous time. And we call that the birth process, and I've just given it notation gamma k plus 1, and a superscript b indicates it's a birth process, and is essentially a point process on x independent of the points that originated from xk. And to get your realization at time k plus 1, you just take the union of the points that originated from the previous time and the birth points, and that gives you your process at your realization at time k plus 1. And you can see by construction it's Markov. Now with the observation model, at time k, again let's just assume that this is a realization of the hidden process. Okay, so each point in here can give rise to an observation. Okay, and if it does, whether the point in here, take x1 for instance, x1 can give rise to an observation. Whether it does or not depends on its position, depends on its location. And so with probability pdxi, the ith point will give you an observation. And if it does, the observation generated by the ith point will be drawn according to some density on y. Okay, and this process is repeated independently for all the points in the realization xk. Now, as for an observation model, we also need to introduce noise, and noise in this context is again, well, it's similar to what we had before. You have a process gamma k c now, c to indicate clutter, of observations unrelated to the ones in xk, and we assume this observations unrelated to unrelated to xk is a point process on y, and you take the union of the observations generated by this and your clutter to give you the observed process. And once again, by construction, you see it satisfies the requirements of hidden Markov model. So the task is essentially specified. For all time k, what you like to do is you want to compute the law of xk given the history of the observation record. And again, just to reiterate what I mean by the law of xk, I mean you want to know two things. You want to know how many points are there hidden. So you need to know the cardinality distribution. So the cardinality distribution is basically defined on, all right, that sum should start from 0, not 1. So that doesn't mean that no reason why xk could have no points, right? So, and if they are n points, you also need to know how they're jointly distributed. Okay, so this is the filtering task, and it's no surprise to people that developing efficient computational tools to propagate this filter is very difficult in this setting. So let's just accept the fact that we won't be able to compute this thing using sequential Monte Carlo particle filters at all for the sort of problems we're looking at. So what's the alternative? So the alternative essentially is an idea proposed by Ronald Mahler, which aims to propagate the first moment of the filter. What is the first moment of the filter? Well, the first moment of the filter is defined as follows. You pick a subset A in X, any subset you want. You count how many points of the hidden process live in A, and you take the expectation of this random variable with respect condition on the observations you've received until time k. So this is known as the first moment. Okay. As a mapping, it'll map all the measurable subsets of X to a number, and you can think of it as an unnormalized probability density on X. And this is going so regardless of however many points there are in the hidden process, this intensity is basically an unnormalized density or measure on X, and it is going to be easier to devise an efficient computational tool to approximate it. Okay, so this is the motivation for why Ronald Mahler introduced this notion of an intensity. And what we need to know as well, we're interested in estimating static parameters, and I'm going to discuss how you do so sequentially. So, okay, so I need to just describe to you basically how you solve the problem in an offline way if you had no restrictions of sequential processing of the data. Now, the reason why I'm doing this is as follows. That application I showed at the start is not solved sequentially by us. Actually, we do use an offline approach. We define a distribution, and then we target the distribution using Markov chain Monte Carlo. The reason we are doing so is because the signal-to-noise ratio in that application is really, really small, and the whole idea is to get the best quality estimates you can. And normally, sequentially, without revising the past estimates based on on information available in the future, is not going to do very well with that sort of data. There's another reason as well. I'm going to talk about estimating static parameters using the sequential idea, and I need to define this distribution because it'll allow me to evaluate certain biases introduced in the estimation of static parameters. So this is the offline problem. If you are given the data until time t, some capital T, and this is an example of the data you're going to get. You can get a record of, at time k, you're going to get a record of all the observations that you received. There are mk of them. It can change over time, obviously. And given this data, you want to know a few things. So if you think of the application at the start, what do we want to know? We want to know how many objects there were that existed from time 1 to t. We want to know when they appeared and when they disappeared or when they died. And death in that application is basically when these objects are bleached beyond detection. And we also, not only that, we also want to know the precise trajectories they took. So all this information that we seek out of the data cannot be answered by this distribution here, because this distribution keeps no information on the ancestry of the points. So I have to define a new distribution that I'm going to target, and doing so will allow me to make the sort of to deduce the stuff I want from the data. So I mean, I'll skim through this really, because this is sort of this is not exactly central to the main theme, but it's needed later. So let me just call nkb the number of births at time k. So every time we introduce new objects in the model, that's how the model is defined. And I define this variable here nk to be the number of targets seen until time k. So basically, you're counting every target you've seen until time k. The state of the ith target at time k is this xki. So by me calling a ith target, there's some implicit numbering going on there. Okay. And also, I'm going to define these indicator variables associated with the ith target. So the indicator variable at time k is going to be either 0, 1, or e. 0 if the target is not going to give you an observation, 1 if it's going to give you an observation, e if it's expired. And I augment these two and call this state zki. So basically, what I'm going to do is I'm going to keep the record of all the targets that have appeared, even though they've expired, in the target distribution I'm going to define. And this is a target distribution. So it looks rather busy, but the idea is very simple. I've got some variables here that will help me decide how many objects I've seen until capital time, capital T. And here is the record. So at time k, I maintain a record of all those objects that have appeared prior to time k. And I just keep them in the state descriptor, and I keep augmenting them with new stuff I've seen. And this is the new stuff. The new stuff is essentially however many came from the previous time, plus the new births, which is what these indices mean, going from nk minus 1 to nk minus 1 plus nkb. Okay? So mind you, some of this could have expired, but that's okay. We just drive our Markov chain into the coffin state. So we define a coffin state and we say, okay, it sits there and it no longer evolves, no longer gives you observations. And this is the Markov process. And I've already mentioned that essentially all targets that have appeared from time 1 to k minus 1 are retained in the state descriptor, and it's appended with new ones. Okay, so this is some simplification of the model. It's not really important. Essentially, I'm going to simplify my inference problem. So I'm going to assume lots of Gaussianity. I'm going to assume that these probabilities of persistence of a target and the probability of detections are independent of location, so just constants. I'm going to assume the intensity of, so false measurements follows a Poisson point process with a homogeneous Poisson point process, which really means, all it means is that the law of that process is specified again by a constant. I'm going to assume Gaussian transitions for the individual objects. Assume a Gaussian observation model for the individual objects. So remember, this is my likelihood. If an object gave me an observation, it gives me an observation according to this likelihood. And there's an appropriate Gaussian assumption for the birth process. So this is the distribution of interest. It's Markov, and this is essentially the law of the process from time 1 to capital T given the observation record. Okay? But the point is here, under the simplified model, we can marginalize out all the continuous valued variables in here. And the task of sampling from this distribution reduces to one of sampling from the posterior over partitions of observations. So what that means really is as follows. You're forming a partition of all the observations you received until time capital T, where partition I will contain all the measurements that belong to target I. Remember, the targets are numbered in accordance with appearance. And in addition, I just sort of using notation here, I will augment the partition with the birth and death time of the target. Okay, so that's basically it. Now we can sample from this distribution. We have not changed our problem. All I've done is I've marginalized out continuous value states, and I've redefined, sort of reparameterized the problem. And this is the prior on partitions, which is inherited by the prior on this Markov, inherited by the prior of that Markov process xi k. And this is the likelihood. It's easy for me to evaluate, and this I've augmented the model with static parameters. Okay, so I can sample from this using MCMC, and you use a Gibbs sampling scheme where you sample the static parameters, condition everything else, and then you sample the partitions. And sampling of the partitions is one of creating new partitions when you create new objects, and augmenting partitions when you think an object is no longer there. It's not a big deal. Okay, and so essentially we can do this, and so we'll keep this in mind for when we come to sequential inference for static parameters. Okay, so I also need something called a Poisson point process, which I sort of mentioned, and let me just define what it is. It's going to feature prominently because using all the properties of a Poisson point process, we can simplify a lot of the derivations of the posterior distributions we're interested in. Okay, so a Poisson point process essentially is characterized by its intensity. So remember, the realization of the point process lives in this state space X. And specify the law of the point process. You don't have to specify the cardinality distribution, the joint distribution of points. Everything is summarized by the intensity of the point process. And this is how you simulate it. You simulate the number of points in the realization by just normalizing this intensity, call it lambda, and you simulate the number of points according to a Poisson distributed distribution. Okay, so you think if there are k points, it will be generated according. So basically, the probability of having k points in the distribution is just given by this. And once you've simulated the cardinality of the distribution, you simulate the joint configuration by sampling the normalized version of V independently. Okay? So you can see how, so this type of process is known as one which has complete spatial randomness because there's no interactions at all between the realization of the process. Okay, so what do we know about the law of this process? What is the marginal distribution of xk? Okay, so if we assume that the birth process is Poisson, so that means every time when you augment new points to xk, it follows a Poisson point process, the realization of the new points. And we know that the evolution of this process here was defined through a thinning procedure, a displacement, and superposition of the new points. That's how I define the law of the Markov point process, of the Markov spatial process. Now, the main point here is a well-known result. You can look it up in lots of books. There's Daly and Ver-Jones. There's Kingman's book. Well, they don't necessarily treat a problem like that. You can just peel off well-known results. It basically says that Poissonness is preserved under independent thinning, displacement, and superposition. So what it means is that if you start off with a Poisson process for the initial distribution with intensity V0, then xk is Poisson for all time, and this is how its intensity evolves. So the intensity at time k plus 1 is basically the old intensity thinned and displaced. That's what this integral is saying. And you add to that intensity the intensity of the process of new points. So we know now the marginal law of xk is Poisson. So let's see now if we can characterize the posterior distribution of a Poisson prior under our observation model. So I'm just going to think of a very simple problem. I say, okay, I've got a hidden process x which is Poisson. I know my observation model. What can I say about the posterior distribution of x after observing realizations of the observations? That didn't sound too right, did it? Okay, so the point is here, this is essentially what I'm saying. Let's just say we got a hidden process x, we observe it indirectly through y, and what we want to know, given this realization of observations, we would like to know the revised probabilities for the cardinality distribution and the revised probabilities for the joint distribution of the points of x. Okay, but obviously we're not going to get this. We're going to get this in a much simpler way. Okay, we're not going to do a brute force approach. And just as a remark, these types of observation models are not unique to tracking. They've also been considered in other applications. And if you're interested in how you get the posterior distribution for this type of an observation model for a prior which is not Poisson, for example, a Strauss process, which is more appropriate for different applications, you can look at this paper where they solve the problem using perfect simulation. Okay, so I'm going to show you the sketch of the proof about the sketch of the idea how you derive the posterior distribution. And to do so, I just need a very simple fact about the Poisson point process. In fact, it's sort of implicit in the definition, but it's worth just going through it. So I defined a Poisson point process before just on x. Now I'm going to define a 2-coordinate Poisson point process. That means each realization has 2 coordinates, one that lives in x and the second coordinate lives in m. Okay, and m, why I've chosen m is because this essentially comes from the marking theorem. So this is called the mark space. And if I want to specify the law of a Poisson point process, I need to specify its intensity, right? That's what I said before. And so let this be basically intensity of the point process whose realization lives here. And now we ask ourselves this question: if we were to observe the first coordinate of this point process, just the first, not the second, and it was declared to us to be x1 to xk, what do we know about the distribution of the second coordinates? So what do we know about the point process which is defined by the restriction to just m? Well, the restriction of the realization to just m. Well, we know everything we want to know. Essentially, we know if there are k first coordinates, then there must be k second coordinates. There cannot be anything else. And the second coordinates are jointly distributed as follows. So basically, the joint distribution of second coordinates is a product form where the second coordinate for first coordinate xi is distributed according to the appropriate normalized version of its measure. Okay? So okay, a very simple fact is sort of implicit in the definition of a Poisson point process. Now let's see how we characterize the posterior. Okay, so here's the idea. What have I drawn? I've drawn essentially just a realization of the hidden point process. Okay, these thick black dots. In this case here is just saying, I'm just saying, oh look, in my hidden process they are essentially 2 points in this realization. And what I've also drawn on the vertical line is the realization of the observations I got. So in this case there are 4 observations. These lines here tell me where these observations came from. So this is telling me this observation came from this hidden point, this observation came from this hidden point. Okay, I should mention one more thing. I'm sketching the idea for how you characterize the posterior distribution, assuming that every hidden point is going to give you an observation. And okay, I'm not making my life so easy. I'm going to say, okay, assume that every hidden point is going to give you an observation, but you also have to deal with false measurements. So in principle, it's not so simple to characterize the posterior. But the appropriate modification of this proof to the situation where not all hidden points gives you an observation is very, very simple, and I won't mention it, but if anyone's interested, you can ask me afterwards. Okay, so what I've done here also is the observations that were not generated by the hidden points, I've given them a mark. What is a mark? I've just associated the second coordinate. So basically I've said, okay, let the observations that are not generated by the hidden points be given a mark delta. And I just choose delta to be a point isolated from x. Okay? So if I were to look at the hollow points now, these hollow points, there are 4 of them, essentially can be thought of as a Poisson point process on this space, where the first coordinate lives in y and the second coordinate lives in, could be either x or just this. And I've done a few things here essentially. I've, if you like, embedded a Poisson process into a larger space. I've flipped the coordinates around and so on and so forth. And I can do that because of the properties of Poisson point process. I can do that. Okay, so we accept the fact that I can do that, and we say, okay, the hollow points now are Poisson point process in this space here. So in a sense, we pretty much answered our question. So what do we know about the coordinates of the second coordinates of the process given the declaration of the first coordinates? We pretty much know how they're distributed. And they're distributed as follows. I mean, this is a rather, okay, this construction essentially, okay, let me just look at this result first. It says that the second coordinates are distributed according distributed accordingly, where the second coordinate of yi is distributed according to a normalized measure mu. This is what I've said. This is the result I said before concerning just a Poisson point process on X cross M. And I've just applied that result to here. Now this measure mu is essentially constructed from all the knowns of the problem. Okay, this is the intensity of the hidden process X. This is how observations are generated, and this is the intensity of the clutter. It's not, the particular construction is not important, but the fact is that we straight away answer our question concerning the distribution of the hidden points given observations. Okay, and you can, a minor modification of this result will deal with the fact when we'll deal with the situation where not all hidden points give you observations. And so I'm just going to summarize this by in this result, which essentially says the posterior of X given the observations is a superposition of two independent point processes, one of which we just characterized, and the other I didn't characterize for you, but I'm just going to say essentially what to derive this result, we've done this bit. To get this bit, essentially what you do is that you break your point process X into two parts. One part that will give you an observation, and one part that does not. And the part that does not give you an observation is still Poisson, and the observations tell you nothing about it, and this is the intensity of the part that didn't give you observations. As you can see, its intensity is modulated by 1 minus the probability of giving you an observation. Okay, so a very simple characterization of the posterior for a Poisson prior in the observation model. Now there are few results you can actually peel off from this, which we will need. One of this is the likelihood, and this is I guess the simplest way I can describe the likelihood by just saying the marginal distribution of y is Poisson with this intensity. So the marginal distribution of y, so basically points that you see are contributed by clutter, and they're contributed by some of the hidden process. Some of the points of the hidden process, and this is the contribution that comes from hidden process, this is the contribution that comes from clutter. And if you know this, then you know the likelihood. Okay. Okay, so we're almost there. We're almost in terms of how I use this for sequential inference. I just need to say one more thing. I mentioned before that what we need to do is that we're not going to propagate the posterior distribution of the whole posterior distribution, but just its first moment. Essentially, which is just this: we need to characterize this expectation, essentially, which is just we count for a hidden process. We count how many of them live in A, and then we take the expectant value with respect to the posterior distribution. Okay, this is what we want to characterize now, and this is given by this result, which again falls out from the characterization of the posterior. Which just says that the intensity of the superposition of two independent point processes is the sum of the intensity. So this is the stuff that comes from the process, which doesn't give you observations, and this is the stuff that came from the part that you characterize given the observations. Okay, so what's new here? This result for the intensity was originally derived by Mahler. What he didn't derive was the full posterior distribution, and also what's new here as well is the derivation of the posterior distribution, which is in my opinion simple and intuitive. And the result for the intensity, so lots of results fall out of which one of which is the result for the intensity, which I said was obvious. Okay, so how do we use this in a filtering context? So here we're going to apply this to sequential inference, and then we're going to talk about Monte Carlo methods for doing sequential inference. So at time k minus 1, we got all these observations until time k minus 1, and let's just assume we have the posterior distribution of the hidden process at time k minus 1 given all the observations, and let's just assume that it's Poisson. And obviously with a Poisson point process, all we need to know is its intensity. So we assume that. So we need to predict this, right? So in a filtering context, we need to do two things. One is prediction and one is update. And we have seen from the fact, basically Poissonness is preserved under the particular way in which xk evolves, and this is the intensity of so basically the predicted process is fully characterized by this intensity, okay, which is what we saw before. which just says that this is the contribution of the intensity from the previous time. Some of which will contribute to time k because of the process of thinning, and then if the part and this it'll be displaced according to f, and this is a contribution by the birth. Things fall apart a bit when you actually go to doing the update step. Right, so with the new observation yk, we've already characterized what the posterior distribution is. That was given by the result before. And we saw it is a superposition of two independent point processes. Unfortunately, it's not Poisson. Okay, it's not Poisson, which means that just characterizing the posterior distribution by just keeping the intensity of the point process is going to break down. So this is an idea Mahler had, which is say, well, why not we just do a best Poisson approximation to the posterior and keep that. So, and the result basically is straightforward. It just says the best Poisson approximation to the posterior in a KL sense is a Poisson process with the intensity of this guy here. And we know what it is. So this is how you derive, okay, I should say that this projection step is not ideal, but is really needed for implementation. And I will show you in slides to come that we can actually use it for inference of static parameters as well, which is something which is sort of overlooked in the literature. Nobody has sort of realized that. So this is the formula Mahler came up with, which we essentially just re-derived, which I think in a much simpler way. He said, well, this is the prediction step, which we know, and he said this is the update step. So essentially the update step here for the intensity comes from the projection result. So you characterize the law of the process at time k, and then you project it, and this is what the intensity of the best Poisson approximation to the filter at time k looks like. Okay, so what we're going to do now is, okay, I guess a point to raise is that this doesn't look so different from your standard Bayes recursion. There is a prediction step and there's an update step. Difference with the Bayes recursion here obviously is the fact that this is not probability density is unnormalized, and there are some parts which are hanging off it, like this additive term here. And the update step, if we just ignore this, okay, because we can, for the purpose of this talk, I mean, nothing really changes in our Monte Carlo implementation, ignoring or keeping this. You can think of this as some sort of mixture of a likelihood. It's not really a likelihood, but you can just think of it as some sort of mixture of a likelihood. So we're multiplying this by some sort of likelihood mixture, and we're going to see how we can approximate this using sequential Monte Carlo. So for the same reasons why you cannot propagate the filtering distribution, and you have to resort to Monte Carlo approximations, essentially the same reason applies here as well. So what we do is you keep a Monte Carlo, basically a particle representation of the intensity at time k. So what does a particle representation, what does it look like? Essentially it's a set of weights and a set of atomic measures. And I can compute any integral of interest with respect to this by using this representation. Okay, and how this differs from a standard particle filter is the fact that the weights don't add up to 1, and what they add up to is the expected number of total targets. Now, that implementation was before the reference here was essentially the equivalent of the bootstrap particle filter for this intensity recursion. And in particle filtering literature, it's pretty much well appreciated that you want to, for a statistically efficient estimator, you want to reduce the variance of the importance weights. And a principal way of reducing the variance of the importance weights is basically this idea of Pitt and Shepard, which is the auxiliary particle filter. And what we can do is we can very simply adapt the auxiliary particle filter to this problem here. And if I were to abstract away the funny looking update equation, what I need to do, given the particle approximation at time k minus 1, what I need to do is I need to be able to compute integrals of interest with respect to this function here. So we can think of this as an unnormalized distribution which has 3 components, 2 of which are discrete, 1 of which is continuous. Second component indexes the particle, and the third component indexes the different terms in the likelihood, the thing that look like a likelihood. And there's a standard way of how you so what we want to do is we want to basically get a particle representation of this distribution now. And what we do is we choose a proposal distribution of this form, and essentially the job is done. All the guidelines you have for coming up with particle approximations for in the filtering case using the auxiliary particle filter, you can apply here as well. Okay, so there's no point spending too much time on it, but the fact that you can come up with an efficient implementation. Okay, so let's look at an example to do with efficiency of the implementation of an auxiliary particle idea. So in this experiment, you're going to see. So I've fixed the realization of ground truth. Okay, I fixed it for the length of the experiment t, which is 40 in this case, or 30. And for that fixed realization of ground truth, I generated observations. And for the observation, so for this record of observations you generate, you apply the auxiliary particle filter to estimate the intensity. And you do this repeatedly. You regenerate observations, you estimate intensity, and you compare the quality of the estimate relative to ground truth. And the whole idea is that if you've come up with a good implementation using sequential Monte Carlo, you should end up with better quality estimates. So here are the box plots for a standard bootstrap implementation. So this thick line here, this black line here, gives you ground truth. It tells you that at time 5 there were 2 hidden targets, at time 10 there were 2, went up to 3, went up to 10, dropped to 2. Okay, so mind you, I'm selling this, so I'm sort of saying that this is a framework for tracking when you cannot propagate the posterior distribution because there are too many hidden states. But a lot of this so what we're doing in terms of improving on the efficiency of implementation, we look at small problems just for comparison, right? Not really big problems. And these box plots here are basically what the estimated total number of targets you get out of the intensity recursion. And as you can see, it doesn't do a very good job at all in estimating the intensity, because it's the total number of targets, because you can see it's all over the place. And with an auxiliary implementation, the box plots essentially pinch the true intensity, the true number of targets, but they're outliers. So how do I explain this? So okay, firstly, these outliers are not severe. Okay, they are just roughly plus minus 1 the truth. The fact that at some times when there are 2, it thinks there is 1 is because the particle approximation can lose track of some of the objects. That can happen. In fact, this is not really my concern. My concern more is the fact, why are there so many more outliers here above the true number? Now the reason for that is not because of the auxiliary implementation, it's because the intensity recursion itself, being one derived from a Poisson approximation, it's sensitive to false measurements that appear in the region where it thinks it's going to see birth of new targets. So when you get a false measurement in a region where you think you're going to see a birth of new targets, and in this implementation the birth of new targets, the prior was very informative. Every time you see in the unlikely occurrence you see a clutter point there, it'll initially think it's a target, but it'll not propagate it beyond that. That's why you have this the outliers lying above. It's basically a function of the intensity recursion itself. Okay, so this is just saying, all this side is just saying is as follows. You can estimate the log of the likelihood at time k, the predictive likelihood, using the same set of samples you had from the particle implementation. Okay, that's the whole message of the slide. Okay, so what do we do with static parameters? Okay, so there are lots of static parameters for this problem, and let's just say these are some of them. We assume we don't know the rate of false alarms, false measurements. We assume it's a homogeneous Poisson point process at this rate. We assume we don't know the persistence probability of a target. We assume we don't know the probability, detection probability. What's the probability to give you an observation? And we don't know lots of things concerning the transition density of the individual targets and the observation density. Okay, so for these experiments, I'm just going to assume they are Gaussian just for the sake of inferring the static parameters of the model. Okay, nothing to do with the fact that the framework is limited and needs its Gaussian assumptions. It doesn't need it because of particle implementation. Okay, the point is that there are lots of static parameters. We don't know this, we don't know this, we don't know this, we don't know maybe this, we don't know R, and we don't know something about the birth process. So what we would like to do is, given the record of observations, we'd like to estimate the true likelihood. But it's not available to us, obviously. But what we have is one derived using the Poisson approximation. Okay, and it looks like that. Of no great importance what it looks like. The fact is that we have it. Okay, and we can compute it once we see our observation record. So what do we do now? Well, we do all we can essentially. We just infer the static parameters by maximizing our approximation. Okay, this raises some issues. Okay, firstly, in models like that, there are lots of unknowns. Well, and we don't know whether, for a finite observation record, whether all the things we want to infer are basically can be inferred. We don't know how identifiable the model is for the finite observation record. Okay, and in the previous slide, I mentioned many things we don't know and we'd like to infer from the data. That's the first issue. The second, well, this is not really, the first issue is not really so important because it's really a function of the problem we're dealing with. The second one is more important. We want to quantify the bias introduced by maximizing the approximation as opposed to the truth. This is far more important. And the third issue is that we only have a Monte Carlo approximation of the likelihood. How do we maximize it? Okay, estimating the error and the bias in the likelihood. Okay, while we cannot evaluate this difference, we have a Monte Carlo approximation of this, which is given by our particle implementation. But where are we going to get a Monte Carlo approximation of the true likelihood? If we had one, at least then we could, we could get some indication of the bias introduced. Well, this is where it's going to come from. That distribution I defined for offline inference is essentially a distribution that shares the same normalizing constant as this one here. That's the online case. Okay, so in the offline problem, we were targeting a distribution with the same normalizing constant. So that means if we were sampling from this using Markov-Chain Monte Carlo, we could use a number of identities to estimate the normalizing constant. The one I'm going to use, or I haven't done it yet, is what we think we're going to do. We haven't done these experiments just yet, but we'll just use one, which is a part sampling identity. Okay, and all this is saying is from the output of the MCMC iterations, you can estimate the normalizing constant. Okay, so in principle, we've got a way of estimating the bias. Okay, it's something we've not done yet, but we're going to do it. Let me just briefly comment on maximum likelihood of hidden Markov models. Okay, if we return now to our standard hidden Markov model, that I started off in the very first slide, nothing to do with point processes. This is just a standard hidden Markov model, and the problem is parameterized by unknowns, by theta, in the transition density, and I'll call the same unknowns in the observation density theta as well. And given the record of observations from time 1 to t, we can use particle methods for maximum likelihood computation. A fact which is known by a number of researchers is as follows. Not only does a particle filter give you an estimate of the likelihood, it can also give you an estimate of the gradient of the likelihood with respect to the static parameters. So what it means now is that you could use a gradient descent algorithm, so you get an observation record, run the particle filter forward, compute the gradient of the likelihood, and use it in a gradient descent method. Okay? Right, so how do we actually do that? In a standard particle filtering context, what we need to do is we need to actually compute gradients of the predictive likelihood. And the basic idea that we use to do so is to essentially introduce the variable xk here before taking the gradient, integrate it out, and then leave the gradient on the outside of the integral. And then we interchange. So essentially what you need to do, if you can compute the gradient of this predictive likelihood with the hidden state introduced as well, then you can compute this thing here by just normalizing this. Just if I integrate this thing over xk, I get back this. My point in showing you this recursion, this gradient here, is just to raise the issue that to compute the gradient of the likelihood, you need, in addition to a particle representation of the filter, you need also a particle representation of the gradient of the filter. Okay, and this is something you can get using the particle filter, and the basic idea is as follows. It's an idea with George and Arnaud Doucet, George Poyagis and Arnaud Doucet. Essentially, what you do is you keep a particular approximation of the filter and its gradient. You keep one of these two. One of them is an intermediate quantity and you don't really need it. And essentially what we do is we keep an n squared implementation. So what it means is that if you have n particles, the cost of computing the gradient of the filter is n squared. And why we actually do that? Well, we've got numerical evidence that a number of researchers have proposed an order n method. The variance grows quadratically with time with an order n method, or with an n squared method, it grows linearly with time. So which means that eventually, for record length long enough, it costs you more, but you'll get a better quality estimate in terms of variance.
So you've done it before. How do you get the particle approximation to this gradient?
Okay, so I should also say that the particle approximation to the filter is used, the same support of the particle approximation to the filter is used for the particle approximation of the gradient. All the change is just the weight.
Okay, the weight can be non-positive.
Yeah, there's some. Yeah, they can be non-positive. Okay, so the point here is essentially that maybe we could use this idea for computing the gradient of the likelihood with the intensity recursion we had before, because it looks much like a Bayesian recursion. But we're not going to do that. There's another idea you could use, which is essentially one of Mike Pitt, which is called the smooth particle filter. The basis of the idea is as follows: when you simulate the particle approximation of the intensity, if you do not change the randomness in the simulation, that means when you have a different observation record, you run the simulation again, the same randomness that you used to generate the first simulation. You can think of this as defining a mapping from the parameters to an estimate. And if this mapping is smooth, you can optimize it using a standard numerical package. And Mike Pitt has a nice idea to smooth the discontinuities introduced in a particle method because of resampling, but it only works for a univariate case, so we're not really going to use it. So what we're going to do is a much simpler method, is we're going to use a finite difference approach, essentially. So this is called, so in a finite difference approach, you've got a real valued function you want to minimize. So j theta over some space, maybe this is rp, this function maps rp, the real line, you want to minimize it. But all you have access to are noisy observations of j for any theta. So you have g theta equals to j plus noise. So what do you do? Well, you can use this sort of gradient algorithm to minimize j, provided you have an estimate of the gradient. And so this is saying my new parameter is the old minus a small step size in the direction of gradient descent. And to form the estimate of the gradient, use a finite difference approach. And there's a cheap way of doing finite differences such that you don't. So, okay, the standard way, if you obey the definition of the partial derivative, and you want to have a finite difference approximation to the gradient at each time, and the parameter is in Rp, you need 2p evaluations of the cost function, okay? Which is very expensive. If you think of this, it is very expensive for what we want to do, because each evaluation of the cost function requires us to browse through the data from time 1 to maybe 1,000 if you have 1,000 data points. So what we're going to do is use an idea by James Spall, which is essentially a simultaneous perturbations approach. And his idea is as follows: you can evaluate the gradient by just evaluating the cost function at 2 points, at theta k minus 1 plus a constant times a perturbation vector, at theta k minus 1 minus a constant times the same perturbation vector. And if you evaluate the gradient at these 2 points, so if you evaluate the cost function at these 2 points, this can give you an estimate of the gradient. And as a scheme for how you generate these perturbation vectors, they are random. It's not really important. The point is here is that you have 2 evaluations of the cost function per iteration regardless of dimension of theta. And I said this is important for what we want to do because this is the cost function we want to maximize. If t is very big, every time we change theta, we don't want to have to wait several minutes for iteration to update theta. And obviously, by using Spall's method, you're not really moving the direction of steepest descent. But he argues, which I've not gone through his argument or his proof, he says that it achieves the same statistical accuracy for a given number of iterations, even though you use p times less, fewer evaluations of the cost function. Okay, so something I've not verified myself. I'm just echoing what he's saying. So okay, so there are some guidelines on how you should choose gamma and how you should choose c, and they are quite standard. What we do is we just use constants. We just choose ck equals to c. We just set a 0, gamma k equals small gamma set b is 0, and we do a pilot run to see to tune the parameters. It's quite standard in stochastic approximation. While for almost sure convergence, you need standard sort of assumptions for the step sizes. In practice, if you want your iterates to move about and not wait forever for them to get to the right part of the solution space, you just use constant step sizes. So here's a numerical example with Nick Whiteley and Simon Gottsill. So we're going to consider an observation record of 100. And for the ground truth, this is how many targets we saw. It is, it ranges from 2 to 10. And these are how many observations we got at each time. So you can get less observations than you have number of targets because some don't give you observations. You can get more than you have number of targets because even though some don't give you observations, you have false measurements. Okay. And so is this likelihood, this approximate likelihood, good for anything? Okay, is it really good for anything given that there's a severe approximation there with the Poisson assumption? Well, just to test this, just so that we know we're not wasting our time, we said to ourselves, okay, let's just assume we don't know one parameter of the model. We plot the likelihood for various ranges of the parameter, the true one included, and we see where it peaks. At the very least, it should give us a peak in the right spot. Otherwise, it means we're wasting our time. And in this case, this is the box plots, and it just gives us a peak in the right spot, which is 1. And what I've changed here is some parameter to do with the observation noise. Okay, so now we're a bit more confident that this thing is going to work. And so far, all we've done is we've just run the algorithm with 3 parameters varying. We're doing bigger simulations now. It takes a bit of time. So what we've varied here is we've varied some parameter of the observation noise, the survival probability of the targets, with what probability they persist to the next time, and some parameter of the state noise that drives the target. Okay, and the truths are shown in these dotted lines here, and these are the estimates you get by using a gradient ascent, using simultaneous perturbation stochastic approximation and the Poisson approximation to the gradient to the likelihood. And you pretty much end up in the right spot. Remember, the gap between here is 0.04. Okay, this is 0.96, this is 1, and the gap here is 0.04. This basically ends up at 0. So the true value is 0.25. It thinks it's 0.23 or whatever it is. And we don't know if this is indeed a bias or the fact that just because you got a finite observation record doesn't mean you can identify these parameters exactly. So what we like to do is we haven't really run the MCMC idea to compare the bias introduced in the Poisson approximation. So basically, I can just summarize by saying the following points. I talked about how you use an idea introduced by Mahler that propagates the intensity of the filtering density in distribution rather than the whole thing, because the whole thing, let's just accept the fact that we can't do it using sequential Monte Carlo. And if you can't do it, what's available to you? You can at least propagate the intensity of the distribution, and you can get an estimate of the number of targets in any region of interest you're interested in, which is not bad. Okay, it is some sort of compensation. And then we went through some simple ideas to derive this intensity recursion. What we also did is that we sort of said that, well, hang on a minute, if this thing is give us, so, okay, another thing is that this intensity recursion does better than existing methods when you in difficult scenarios. Okay, so when you have many of these hidden targets, lots of clutter and things like that, you get a much better estimate using these ideas than you do with a standard approach, using a MHD algorithm and so on. And then we also said, well, actually, there's an overlooked potential here. While I'm not necessarily condoning ideas, I mean, I'm not necessarily saying this is solving the problem. It's not. But okay, given that it gives us reasonable estimates for the expected number of targets, maybe the likelihood derived from it can give us reasonable estimates for the static parameters. And in this case, it does. And you can handle hundreds of time points in MATLAB minutes, as opposed to the MCMC idea I talked about before, because for observation record of 30 for that data involving the live cells, it takes us hours to get Bayesian estimates of the static parameters. This one is an order of minutes. Okay, so these are the plus points. The bad points are the retaining the Poisson approximation after the update step is not ideal, and this does not in any way solve the problem. Okay, it's not the problem that we set out at the start, very ambitious. Oh, we're going to do filtering for spatial point processes. We haven't really done it. Okay, it's just a very modest step in that direction. And what's indeed needed is a particle approximation of the full posterior. Maybe not all scenarios, but in some scenarios we actually need it. And that's the essence of the talk. Thank you.